Conservation of linear momentum. The principle of the conservation of linear momentum states that the total momentum of an isolated or closed system of colliding bodies remain constant. That is, if two bodies collide in a closed system, the total momentum after the collision is equal to total momentum before the collision. The principle of the conservation of linear momentum follows from Newton's second and third law of motion. When a billiard ball A is at rest on a billiard table and is struck by another billiard ball B, after the collision, both balls will move. Ball B moves with reduced speed, while A, which was initially stationary, now acquires a velocity. Their direction also changes. Neither ball continues in exactly the same direction that B was originally moving. During this collision, each ball experiences a change in momentum. Their masses are ma and mb for A and B respectively. Their velocities before collision are ua and ub for A and B respectively. Their final velocities after collision are va and vb. Momentum of ball A before collision is maua and after collision is mava. As a result of the collision, the change of momentum of A is mava minus maua, while that of B is mbvb minus mbub. When two bodies collide, the force on A is equal and opposite to the force on B from Newton's third law. These forces act for the same length of time t, so the impulse on B due to A is exactly equal and opposite that on A due to B. Therefore, impulse on B due to A Ft is equal to change of momentum of B, which is equal to mbvb minus mbub. Impulse on A due to B minus Ft is equal to change of momentum of A, which is equal to minus bracket open mava minus maua bracket close. Equating the two equations, mbvb minus mbub is equal to maua minus mava. The equation becomes maua plus mbub is equal to mava plus mbvb. Remember that momentum is a vector quantity. The sign indicates the direction of motion. Application and examples of conservation of linear momentum. Walking. A person walks by pushing with his or her foot against the ground. A person walking is actually pushed forward by the reaction force of the ground on him and not by his own push on the ground. Newton's cradle. When one ball swings and hits the others, the momentum is transferred through the line, causing the last ball to swing out with the same force and velocity, illustrating conservation of momentum. Firing a gun. When a gun fires a bullet, the bullet moves forward with a certain momentum. The gun recoils backward with an equal and opposite momentum of the system. Gun plus bullet remains zero if it was zero initially. Jumping from a boat. When you jump from a boat to a dock, you push backward on the boat to launch yourself forward. The backward momentum you give the boat is equal and opposite to the forward momentum you gain, keeping total momentum constant. Jet and rocket propulsion. Fireworks rockets and space rockets both work by burning fuel to produce fast-moving hot gases. These gases shoot out of the back of the rocket at high speed, and because of momentum must be conserved, the rocket is pushed forward with equal momentum in the opposite direction. Even though the mass of gas released each second is small, its velocity is so high that it gives the rocket a large forward push. Space rockets carry their own fuel and oxygen, so they can burn fuel even outside the Earth's atmosphere. Jet engines works on a similar principle of producing a high-speed jet of gas, but the way they get the gas is different. A jet engine sucks in air from the front, compresses it using a turbine compressor, mixes it with fuel and burns it to create a high-velocity exhaust jet. The compressor is powered by a smaller turbine driven by the exhaust gases. To start the engine, a strong starter motor is needed to spin the compressor and ignite the fuel. Rockets can operate in space because they carry their own oxygen. Jet engines cannot because they need air from outside to function. The example of conservation of linear momentum and Newton's third law sound similar, but they are actually talking about completely different situations. For example, using rocket propulsion. When a rocket fires, it pushes hot gases backward out of its nozzle. According to Newton's third law, this backward push on the gas is the action, and the gas instantly pushes the rocket forward with an equal and opposite reaction. That's why the rocket starts moving. At the same time, conservation of linear momentum is also at work. The gas moving backward carries momentum with it. Since no external force acts on the system, the rocket must gain forward momentum to keep the total momentum unchanged. Therefore, initial momentum is equal to final momentum. In summary, Newton's third law talks about forces acting at the same time during the interaction, and it's always true whether external force exists or not. Momentum conservation talks about motion and momentum before and after an event, and it only holds when no external force acts on the system. Example, a man of mass 72 kg jumps off a stationary trolley of mass 90 kg with a velocity of 3 meters per second. What is the initial recoil velocity of the trolley? Given mass of man m1 is equal to 72 kg, velocity of man after jump v1 is equal to 3 meters per second, mass of trolley m2 is equal to 90 kg. Initial total momentum is equal to 0 since both the man and the trolley were initially at rest. Applying conservation of momentum after the jump, m1 v1 plus m2 v2 is equal to 0. Recoil velocity of trolley is negative since it moves in the opposite direction to the man's movement. Substituting 72 times 3 plus 90 times v2 is equal to 0. 90 v2 is equal to minus 216. Making v2 the subject of the formula, v2 is equal to minus 216 divided by 90. v2 is equal to minus 2.4 meters per second. That means the trolley recoils with a velocity of 2.4 meters per second in the opposite direction. Try this one. Share your thoughts with me. Make sure you like, subscribe, and share.